antiderivatives. Unlike in an antipasta salad, which does have pasta in it, the antiderivatives take a derivative and get rid of them. So we're turning them back into the original function. And so the main game is, if you recognize a derivative, well, tell me what function it was, right? Like if I gave you y prime is 2x, right? I'm assuming you could just see right away what we had before. We had some kind of y equals what?
X squared.
Exactly.
Plus like a constant or something.
Exactly. The constant thing I didn't think you would know right away. But remember, like if I look at the family of functions for x squared, right? X squared plus 4, x squared plus 3, x squared minus 2, right? The slopes, right, let's say at 1, on all of them are the same. So no matter what constant is there, the derivative is still 2x, okay? So when we're doing an antiderivative, we want to make sure we bring back to life that constant. And notice that constant could be 0, right? This is called the constant of integration. And so eventually we start calling these antiderivatives integrals, okay? Integrals. So the constant of integration. So the trick is, all right, that whenever you're finding a general integral, okay? So there's two types of integrals: a definite integral. When we do that one, we don't care about the constant, and just a general integral, or an integral where we want to make sure we include this constant. Now, what's really nice about this section and all of chapter 5 is that when I find the antiderivative, when I take an integral, I have an answer, and I can check it in the back of the book or on the test by taking a derivative. I take a derivative of the answer, right? So notice that d dx of x squared plus c is equal to 2x plus 0, right? It's 2x. And I get that original answer back, right? The original question back. What's the derivative? Oh, I got it. What's the antiderivative? Okay, I got it. And I can double check easily and quickly, right? And this is why chapter 3 is so important. Our main focus in Calc 2 is antiderivatives. So everything we did with derivatives in Calc 1, we're doing with derivatives in Calc 2. Okay, so that means just, all right, how do you find this derivative? How do you find a derivative when it's a chain rule? How do you find a derivative when everything else fails? That's the tough section. Applications of derivatives, right? And so, and a brief intro to differential equations. Of course, differential equations, you'll see derivatives in the equation like variables, right? And again, we're talking about there, a bunch of things are changing. Can you find the original function that's controlling everything, right? So I tend to make that section really easy for students because not a lot of you are going on to DiffEqs, right? Only my engineers, including computer engineers, right? But I don't think I have any computer engineers here. Am I correct?
Used to.
Okay. So the computer engineers, I'd say take linear before DiffEq. Okay. But none of you here. Okay. So that's fine. So antiderivatives, they're kind of fun. I think derivatives are fun. I don't know if you're feeling more confident with them or hate them. But it's a puzzle, right? It's a little brain teaser. You have to have strategies. You have to have your shortcuts written down. You have to have your shortcuts with a complicated interior written down. You should have them memorized, right? And then you have a bunch of little tricks that you kind of know. And so we're going to do the same for our antiderivatives. Okay, so let's do another one. The main thing in my antiderivative process is identify a derivative that you know, right? So, for example, because I hound you with this one, right? 1 over 2 square roots of x, right? If that's my derivative, can you quickly tell me what the original function was?
Root x.
Yes, plus c. I always want to have that constant of integration, and I will forget it a couple times. Remind me if I do. You might forget it, and if you do on a test, you'll forget it on every problem. This, by the way, this material is not on the Chapter 4 test. Okay, so just taking a break for a Friday, but we have to do it, so it's still on my checklist of things I have to do. For example, in the textbook, for this particular section, I like the following problems.
Professor, when finding an antiderivative, do we always just put plus c?
Yep.
And we don't take any steps to find what c is. We just
yes, there are a couple problems like that, and I'll do one of those today, where I give you a second derivative and a value of the original function, and then you've got to find, in that case, c and d. So you're going to integrate twice, and you're supposed to fill in. I'll do one like that. That's a good question. But remember, in our original lives, I just gave you the square root of x function, but that was still square root of x plus 0. So I want to still account for that plus 0 possibility when right? In fact, if y prime equals 0, what's y?
1?
Yep.
Or c?
Well, no, that is, so in this case, I wouldn't put plus c, right? Because this is a constant, right? So not
Okay,
1,
yeah.
not 1, but c. You're right. It should be c. And if I said y prime is equal to 3, what am I saying for y?
Some value of x?
3,
C?
yeah, 3x plus c, right? And mx plus b always turned into this slope when I took a derivative. So I like problems 1 to 35. 4.8 suggested homework. (1 to 35). Odds, of course, because that's what I gave you the answers to. But what's nice about this is that you can take your answer and do the derivative of it and get back, right? So it's almost impossible for you to get anything wrong on this next test. The worry is you get a derivative wrong and the rest of your work is wrong. But what I try to be showing you, take your function, graph it, take your derivative, graph it, make it at least feasible, right? If it's feasible, if it seems like it's working, right? Meaning when the function's increasing, the derivative's above the x-axis. When the original function is concave down, the second derivative is below the x-axis, right? So all those little things that you could be double checking yourself before you finish, right? The 2 or 3 page problem, just to know. And then in that case, most likely you're only off by a constant. And so I wouldn't take points off the additional work after you found your derivative and it was only off by, a 2 kind of thing, right?
How far is Tacoma Park from the metro station?
I walk it all the time from the Red Line Tacoma station. Yeah, it's I think it's half a mile. There was a bus.
Okay.
The bus is lame, though. The bus is
Yeah,
never there.
I wouldn't do the bus.
Yeah.
I don't do buses.
Okay. Yeah, it's not a bad walk. I mean, of course, if it's raining, it sucks. But and the thing about that position too is, like, if you were stressed out and said, "Oh, I've got 2 exams this week," they would say, "All right, don't come in today." They would do that. We understand student stress for sure, because we've all been through it too.
Yeah.
All right, let's do a couple of other tricky ones. So if you remember, if y was x to the n, we got y prime as n times x to the n minus 1. And so if you think about the process of taking a derivative, to undo it, it's the same as the process of putting on your socks and shoes. When you undo it, you can't take your socks off first. Well, you can, but it could be painful. So you have to think about, right, what am I doing when I take a derivative? I'm multiplying by the current exponent, right? And then I am reducing the exponent. Right? So if I'm going in reverse, so for example, y prime is 2x cubed, right? What am I going to do? I'm going to not start with the coefficient. I'm going to end with the coefficient. And I'm not going to multiply, I'm going to divide, right? Because I multiplied to get the coefficient in my derivative first. So I'm going to divide to get the new coefficient in my antiderivative. And remember what I did second in the derivative. I subtracted 1 from the exponent. So what am I going to do now? I'm going to add 1 to the exponent first. So I'm going to go 2x to the 3 plus 1. I'm adding 1 to the exponent, and then dividing by that new exponent, and then adding my constant c.
Sounds like it's going to get quote-unquote fun once you're dealing with
we get
original derivatives
exactly.
that have stuff under.
Yes, when we get to chain rule derivatives, which is section 5.4, our very last section, it's quite complicated. In fact, we can't even finish it in Calc 1. We finish it in Calc 2. And then those methods start failing. So we learn about 12 different methods to take antiderivatives in Calc 1 and Calc 2. And then those fail. Thank you. Who said that? Noah. Thank you, Noah. It's not y prime. I already had a y prime. There we go. And then I want to, of course, just clean this up. So y equals what? X to the 4th over 2 plus c. Right? So this is the power rule for antiderivatives, right? We had so I'm kind of going through my list of our very first derivatives, right? Derivative of a constant is 0. Derivative of a mx plus b is an m. Derivative of x to the n is n times x to the n minus 1. So I'm going through that list, but in reverse, right? Doing each problem, starting with the derivative, trying to get to the function. A couple of interesting ones. We had our sine and cosine wheel, right? So I had a ABC, MN, OP, QRS. And when I was doing derivatives, I'm going this way. When I'm doing antiderivatives, I'm going the opposite way. So if I have the integral of cos of x, if y prime is cos of x, that's what's coming, the integral. If y prime is cos of x, follow my arrow in red, cosine turns into what? Right? Follow the arrow. I don't go past the negative. So antiderivative of cosine is sine. So antiderivative of cosine of x is sine of x plus c. And of course, if y equals sine of y prime equals sine of x, notice follow that red arrow around the circle. I go past the letter n for negative. So I get y equals negative cos of x plus c. And you'll often see the book write it like this, just so I have one less SIGN to write. Right, in that second version, I don't have to write the plus symbol.
Didn't when we have like an original y function of cosine, it becomes 1 over sine x.
You're.
Or which one am I remembering?
I don't know. Not sure.
Wait, hold on. Let me get back.
Yep. So we want, all of our. So if I said to you y prime was secant x tan x, right? You're going to say to me y is what?
Never mind, I'm thinking of tangent because 1 over whatever. Yeah.
Okay, no worries. I thought you were thinking of some reciprocal thing. So derivative of secant, right, is secant tangent. So secant x plus c here. So you see how good you need to be at your derivatives. In fact, all the way through diffie-qs. You will do, computer science students will do some derivatives in linear. So not much. We really are asking. Linear algebra is mostly algebra, right? So, but there is some applications to calculus and linear algebra. So, and again, of course, the bio students are released from hell. Chem students. We need the integrals for both bio and chem. For chem, I think. I need Calc 1 intervals for chem, I think. I don't know. I didn't take. I had one day of chemistry in high school. They said there'd be homework every day. I asked for a pass to the bathroom and never went back. What a slacker.
Chem is fun. It's like applied math.
Yeah, I think they had fun with it in Breaking Bad. 4, 8, 12, 15. They get tricky, okay? And there's a couple of tricks that we need to think about. Before I get to the tricky ones, let's do a couple more real simple ones. So, for example, oops, I keep writing the integral. By the way, if I say y prime is 1 over 2 square roots of x, implies y equals square root of x plus c, I'm going to be writing that as the integral, and you can see kind of a letter S there, of 1 over 2 square roots of x with respect to x is equal to square root of x plus c. So when we're talking about antiderivatives, we'll use this form. And when we start getting a little bit more sophisticated, we'll be talking about integrals, right? So this one I would call an antiderivative. Same though, of course, right? And this one is the integral. And we're going to learn where that kind of curly thing that looks like an S comes from. Of course,
this is like our teaching our power rule first, and then going to our x plus h limit definition.
Yeah. We kind of don't go back to that limit anymore. We needed that limit to teach derivatives, right? So, but
yep.
we do, and you'll see we do something completely different. We're going to do area. So, by the way, that whole limit was slope, right? So a derivative gives you a slope of a function at any point. An antiderivative gives you area under the curve. So what we're going to be doing, and why is this guy is a sum. We're going to be adding up areas and under the curve, and that's what gives us the antiderivative. So it's a really interesting relationship. Taking a derivative gives you a slope. Taking the antiderivative of a slope gives you area under the curve. Weird, right? But I guess so is the concept of God. Kind of hard to believe. And I like to swear to God I'm an atheist. Get it? I swear to God you're an atheist. I'm only joking about that, but it's funny. It's like getting your left arm to be ambidextrous, right? Okay.
True.
So if y prime is e to the x, we know that y is e to the x plus c, right? If y prime is 1 over x, who's got it? What's y? Nice, ln of x plus c, right? ln of x plus c. And this is actually wrong, but it's the guess I would give, right? So that's wrong. The actual answer is y equals the ln of the absolute value of x plus c. And let me see if I can explain that, okay? So you can definitely see, if we go back to derivatives, if I give you the ln of x function, right? You can see my domain is restricted, right? And so my domain here is only positive numbers. I can't put a negative into ln, right? I can't put 0 into ln. So when I'm dealing with its derivative, right, y prime is 1 over x, I don't care about the piece of 1 over x that's got negatives in it. It can't happen anyway. It's not going to give me a slope of ln because there's no ln doesn't exist on that left-hand side of this of this grid, right? So, but if I start with 1 over x, right? I'm starting with 1 over x. This is my, right? This is what I'm saying is my derivative, right? Now you see I have to include the positives and the negatives, right? Because they're in my domain. So, and you'll understand a little bit later what we're doing with these antiderivatives. But now when I consider the original function, because I have pieces on both sides, I have to somehow manipulate my function to say that now y equals the ln of the absolute value of x plus c. And by the way, that function looks like this. It's kind of a symmetrical, right? So this is y equals ln of absolute value of x. So that's our first one that's a little bit weird that we have to write down. We have to memorize, of course, right? And it will come into play more in DiffyQs, a little bit in Calc 2, but for the most part, I will stay away from having to have this absolute value in there.
There's always a ton to memorize until you know all the rules that make the memorize come up.
Exactly, and that's what you're trying to do. You're trying to memorize things until suddenly they click, and I kind of feel like that's life a little bit. You got to just kind of accept, and then eventually you realize why am I tortured by this, and you know, it gets easier. Definitely.
You get there in the end.
Yeah. So that's a bit of a strange one. Let's look at another strange one here. like this one, if y prime is x squared over 1 plus x squared, I want to, first of all, note that, and this is a special note, when you see that long division will work, we want to long divide before we integrate, before we take an antiderivative. So meaning if I'm polynomial over polynomial, and the power of the numerator is greater than or equal to the highest power of the denominator, I would like to long divide that, okay? So x cubed upstairs, x to the 7th upstairs, right, et cetera, I'm going to long divide on this one. So I want to take x squared plus 1, long divide into x squared. And so I'm thinking x squared times what will give me x squared? That's 1, right? And then I come back and multiply. I get x squared plus 1. I change my signs and add. So I get a remainder of negative 1. So this y prime really can be written as 1 plus negative 1 over 1 plus x squared. And then I should recognize the antiderivative. So our first trick is, if you can long divide, okay? So anybody see why now?
Hold on, let me see.
Can you repeat that again? Sorry.
Yeah, well, I'm asking, if I gave you this original function, you should be able to see the antiderivative, right? But I gave you something that you could long divide with. And so the trick is to, if you can long divide, okay? But anybody see the antiderivative here yet? What did I take a derivative of to get 1? Good, x. Do you recognize the other piece? Do you recognize this derivative? You should.
We did have a big problem that took that as the answer.
Yep, arctan of x. Right, so x minus arctan of x all plus c.
This is why they have to teach trig.
Yes, well, trig is very important. Trig is
it's
all rotations. So left to right, up and down. So trig is very
important.
Yeah,
the functions are naturally very important.
Yes.
But it's also necessary in the case of functions that take these forms where it's going to go to trig identities after.
Yes, and that's one of the most difficult parts of Calc 2 is when we start doing something called trig substitution. We get some kind of version of x for our derivative, but we can't figure out the antiderivative unless we turn everything into trig functions. So there's a bit of this turning things into trig functions into x functions of x and vice versa that will kill you if you can't do trig. Right? When I'm drawing those triangles and you hate those triangles, Calc 2 is going to be hell.
I need to do more triangles.
Yeah. Did you do has anybody done the trig course with Khan Academy? It's really nice. It's, I don't know, 4 to 8 hours of work.
Honestly, what I need to do is go back to our trig homeworks and do more problems of them.
Yeah, book is kind of weak. I would rather you go back to the pre-cal book and do all 4 sections of the trig stuff there.
That's true too, yeah.
No, it's not 4 sections. It's 2 chapters. No, it's 3 chapters. I think it's chapter 6, 7, and 8. And do all of those over in the pre-cal course.
That would be a good suggestion for after class, for sure.
So long divide is one of our tricks, right? And divide and conquer is one of our tricks. Let me see if I can find a divide and conquer problem. Oh, yeah, sure. This is number 10 in the textbook, 4.8, number 10. So I've got y prime.
Oh, wait, did we get our answer for the last question?
Yeah.
Oh.
Done. Derivative of x is 1. derivative of arctan is 1 over
Okay.
1. Yep. 1
I
over,
just forgot to look at it.
Yep.
I looked over it.
Yep, no problem. So divide and conquer is one of our little tricks that we use quite a bit. Another one is to add 0, right? You'll see me adding 0 when I do some things in chapter 5. So minus 4x cubed plus 2x to the 6th over x to the 6th. So whenever I see a multi-term numerator, I can divide and conquer. And that is take one or more terms of the numerator over the denominator plus the remaining terms over the denominator, right? In this case, I'm going to completely divide and conquer. Right, simplify as much as I can.
And that is already a lot of division.
Yeah.
So you're just kind of breaking it up. Okay,
Yep, divide and conquer. In this case, I take every term over the denominator, right? And now you can see I just have a bunch of simple power rules and or just a mx plus b, right? So this is going to give me, is everybody okay here with what I just did? I did a couple steps at once, yeah.
The cheatsy way, you made all the over x6.
Yes, because I'm going to have to add to the power, divide by the new power, right? So for my y, I get 5x to the negative 6 plus 1 over negative 6 plus 1 minus 4x to the minus 3 plus 1 over negative 3 plus 1 plus 2x plus c. And yeah, go ahead.
Do we have time to try one on our own on the next question?
Of course. Yeah, I mean, I would say, like I'm saying now, you're not copying me. You should be racing me, right?
I'm always too slow for it, Professor.
Right, but even if you're...
Except when I know it already.
You can still walk a marathon. You can still... Doesn't mean, I'd rather you be trying it. And then, of course, rewriting it later. When class is over, you should rewrite all the problems that I've done, right? So we get...
That's actually a good point.
Yeah. So 5x to the minus 5 over minus 5 plus 4 x to the minus 2 over 2. I canceled the negatives already there. Plus 2x plus c. Then we get negative 1 over x to the 5th plus 2 over x squared plus 2x plus c. And I would probably just put the c out front. Now, what have I been saying all along? If you have fractions within fractions, get me a single fraction. I'm gonna ease up on that a bit with integration. I'm not finding zeros of integrals, so that's why I'm stressing that in chapter 3 and chapter 4, because I have to find the zeros, right? And it's so much easier to find the zeros if things are factored, but we don't need that when we're integrating. Okay, you'll see what the piece is that's so valuable in integrating. It's finding areas.
You could technically
as like 2 to the, or like negative exponents. Do you prefer this?
Positive, yeah. We like to write everything as positive exponents. Yep. Go ahead, Jess.
I was gonna say, technically you could write that function as over x to the 5.
Yes. Yes. And it doesn't really get much better. And so we typically would do that, but leave the constant alone. So
Yeah.
I would get 2x cubed, sorry, I'd get 2x to the 6th plus 2x cubed minus 1 all over x to the 5th, right? And c minus that, or plus that, yeah. So it doesn't, I don't care. I don't care. And I know why I'm not going to tell you why yet, because it's just know that rule is going to get a little bit more relaxed. And then, of course, if I'm double checking this, it's a lot easier to take the derivative of this one to double check it, right? So just know.
Yeah, because you already see how it's broken up.
Yes. So this rule that we had of always getting me a single fraction completely factored is going to be eased up on a bit as we move forward, and in Calc 2.
Okay.
Yeah.
I'm sure there's certain branches of certain types of things that you might deal with where you still do want this sort of stuff, but it's definitely easier to think about it when you just leave the answer how we found it.
Correct. I'm not seeing anything. Oh, I wanted to do just one more type of problem that Nahom was referring to. Is, do you ever have to find C? And the answer is yes. It's really for this kind of purpose of I always say it's war inspired. I'm going to shoot a rocket up. Of course, it travels in a sense of a quadratic, and I'm going to adjust the C depending on where I want the bomb to land, right? We could make it a little bit more wholesome by saying it's a basketball, and we're shooting a shot up in the air, and it's got to land. We want to make sure it at least is over 10 feet when it goes to the basket, right? Kind of thing.
It isn't like the easiest way to change the destination of a quadratic, though, to change the zero, not to change the
exactly, and that's the C.
Linear slope.
Yes, but we're working this in kind of reverse, so we want to find that C. So let me write one, and it'll be easier.
Okay.
Right? This is 4.8, number 24.
Because I'm just thinking about that. It's like it'd be awfully inefficient to raise where your function is when you can just shift it over a little bit.
Yeah, but if it's not high enough to hit the basket, you have to shift it up. Yeah.
That's true, too.
So I've got 8x cubed plus 12x plus 3. And I know that f of 1 is 6. So Nahom was, I think you were kind of saying this, don't we need some information in order to figure out what the constant is? Yes. So if I give you a derivative, I need some information about the original function. If I give you the second derivative, I need information about the first derivative and the original function, et cetera, down the line. So every time I add a new variable, I need a new equation, right? So this one is find y, right? And not only find y, but find c, right? So first of all, f of x would be what? 8x to the 4th over 4. Did you see what I did there? I can do this one pretty quickly because I can just add 1 to the exponent and divide by the exponent. What's next? Plus 12. Jesse, it's your turn.
Oh, hold on. Let me think.
Remember, I have an x to the 1 there. So what's it going to become? What am I doing to my exponent?
Is it, no, it's not doing ln.
No, it's 12x squared
Yeah,
over
it's just
2.
getting...
Add 1 to the exponent, divide by the new exponent. What about the 3? What does that become?
Okay.
The 3 becomes 3x. And
It's 3x.
good. And then the constant c. Good. See? You can race. So I got f of x is 4x to the 4th plus 6x squared plus 3x plus c. And if I plug in f of 1, I'm supposed to get 6.
I'm sorry, Professor. My mind was thinking about metros, not math.
That's fine. So obviously c is... Go ahead.
Isn't that 2x to the 4th? Because you're dividing by 4.
Oh, thank you. Yeah. Oh my gosh, Robert. What the hell? Wait, what? What? 2x to the 4th, yes. Thank you. Silly Robert. So it looks like c is negative 5. So now I can write f of x is 2x to the 4th plus 6x squared plus 3x minus 5. Done. Those are all pretty damn easy.
You should be saying, oh yeah, I put that mistake in there on purpose.
Yeah, that's what my teachers used to say.
Make sure you guys were awake.
I lie enough at night, so I don't like to lie in the day.
So where did you get the 6? Basically.
They gave it to me. This was the original problem.
Oh, okay.
Yeah.
Okay.
So they have to give me some other information if I'm going to find out what the constant was. Yeah.
Yeah, even if you have a single point, that's enough information.
Exactly. One equation, I need one more bit of information. Two equations, I need 2 more bits of information. Right?
2 equations? When are we going to deal with 2 equations?
If I give you a second derivative. Let me do one like that.
Oh, okay. Okay, yeah. Because you're doing an antiderivative twice.
Exactly. And so I'm going to have a constant c in the first one and a constant d in the next one.
If you only had 1 point of information, you could only tell it's either here or there, or
Right.
It's here or there.
Right.
Probably like 4 different places or 2 different places at least.
Yeah, here. So let's do this one. This is number 31. And I've got y double prime is equal to sine x plus cos x. And I know that f of 0 is 3. And f prime of 0 is 4. So we want our wheel, right? We want our wheel, cos negative sine. So the antiderivative of sine is cosine. The antiderivative of cosine is
Negative sign.
Negative sine, all plus c. And I would like to find c right away, so I'm going to use this information, right? I'm going to use this information first, right? Because I've got my first derivative now. So I know if I plug in 0, I get 4. So cos of 0 minus sine of 0 plus c equals 4. Cos of 0 is 1. Sine of 0 is 0. So I get c equals 3. So there's my first derivative all set up with, right, the c being found. Now I could leave that as c and then do my second integration, second antiderivative, and then find c and d. Either way, do them both ways maybe. All right, so now that is everybody okay here?
You swapped the places where the cosine and the sine went to. That was just a simplification in your head.
No, I did not. I took an antiderivative of sine to get cosine. Antiderivative of sine is cosine.
Oh, we're already on the second step.
Yep.
I thought, okay, never mind.
Yep, no problem. So now y, again using my wheel, antiderivative of cosine is negative sine. antiderivative of negative sign is negative cosine plus 3x plus a new c, or a d if you want. I don't care what letter you use. Use any letter you want.
C sub 1.
Yep, c sub 1, c sub 2, fine. And now I'm plugging in this information. F of 0 is 3, right? So I get negative sine of 0 minus cos of 0 plus 3 times 0 plus c equals 3, right? Well, sine of 0 is gone, 3 times 0 is gone. Cos of 0 is minus 1. Negative cos of 0 is minus 1. So it looks like c is 4. And now I can finally write y equals 4 plus 3x minus sine of x minus cos of x. Done.
This one is nice because sine values of 0 go nice and easily into ones and zeros.
Hopefully.
For now.
So would you take points off if there's like negative sine of x minus cosine of x?
No, I would not. It's still correct. It's just not as pretty in my opinion, but you know.
Oh, the evil professor would give the F0 at a point where it's calculated like it'd be like F, pi over 2.
Oh yeah, that's what I would do. I wouldn't put a 0 in, because some of you still struggle with trig so much that you can't tell me sine and cosine of like 7 pi over 4, right? So we got to get that stuff cleaned up. We have to get that stuff cleaned up before we move on. There is kind of an understood piece of that. We just went through COVID. We probably all had trig and pre-cal during COVID. And some teachers let you get away with anything, or just, were frustrated by the whole process and graded in a way that it's a horrible situation for y'all, right? Thank God it didn't happen to you in 2nd, 3rd, 4th grade. Thank God it happened to you now when you're a little bit more sophisticated. But imagine having COVID when you're learning fractions and never being able to do fractions for the rest of your life, right? That's going to happen. In about 8 years, I'm going to have students in calculus that can't do fractions, unless I'm rich or dead.
Yeah.
Well, go ahead.
My mother teaches she's a preschool teacher, so they have occupational hazards because they're like the first people that really want to go back to teaching because they need to.
Yeah, you can't teach it. It's very hard to teach this way to a lot of students, even college students. It's not for everybody. I couldn't have done it. I would have dropped out. And then I would have said I would have gone to Europe or something for a couple of years and, just travel, but you couldn't do that either.
Yeah. Not much. Not many ways out of it.
After my associate's degree from community college, I went to Paris. After I graduated undergrad, I went to China and Hong Kong. So I used to love just go somewhere and experience it.
Hong Kong's a different place now as well.
Yep.
Oh, I think you still have the recording going.
Yeah, I do. Doesn't matter.
Oh, okay. All right. Well,
not giving away any secrets to life or. So we're done today, right? Have a great weekend. Get some work done. Okay.
Good morning, Professor.
Good morning, Martins. What's shaking?
Yeah, I was having internet issue. That's why.
No problem. I
called
recorded all the new stuff.
Wait,
Okay.
yeah, can I find it like tonight?
Yeah, I'm gonna upload it right now. It should be
Please.
there in about 2 hours. Do you know where to go to find it before I paste it somewhere?
Oh, is it in the syllabus? Can I find it in the syllabus?
No, I sent an email to you where my link
Oh.
to Robert Kuhar videos on YouTube.
Oh, okay,
Don't you
okay.
remember?
I think